Dr. S. Shankar is a professor, Department of Physics at Madras Institute of Technology, Anna University, Chennai. His area of specialization is solid-state physics. He has guided more than 10 PhD scholars. He has published more than 50 national and international research papers. He has 28 years of teaching experience.
Welcome to UGC lecture series. These topics are concerned with solid-state physics, and we are going to see episode number 7. And the subject is about magnetic materials. We have seen in earlier lectures about diamagnetism and paramagnetism and paramagnetic theory and the corresponding susceptibility we have worked out. And today we are going to see about ferromagnetism and the corresponding mean field theory proposed by Weiss. The objectives of the present talk are first to understand the difference between para and ferromagnetisms, then to understand the nature of internal effective magnetic field development, and then to derive the so-called Curie temperature and Curie-Weiss law. We know that the magnetic moments originate on an atomic scale from the orbiting and spinning electrons. These effects are also influenced by the particular electronic configuration of the different elements. Electrons actually have two contributions for magnetism, one from spinning motion and the other from orbiting motion. The largest magnetic effects are due to spins of electrons in matter indeed, apart from their orbital moments. So, the orbital moments play a major part as well, but when there are uncompensated spins present in a molecule, the orbital contribution becomes much smaller. Now, here we see the sketch of how the spin arrangement is there in transition metals, because altogether spin arrangement results into different types of magnetism in materials, and particularly transition metals play a major role in the magnetic properties. The electronic configuration, how it is arranged in materials, is sketched over here. 1s, then 2s, then it goes to 2p, 3s, then it goes to 3p, 4s, and so on. Now, coming to the spin arrangement, we have s electrons arranged like this, and here we have uncompensated spins, for example, in Cr, and in scandium we see here one uncompensated electron here in 3d, but 4s electrons do not contribute for the spin because the net spin is 0 here for 4s, and so on. So, this gives an idea of how transition metals contribute for uncompensated spins and thereby magnetism development in such materials. Then about spontaneous magnetization, we have mainly 3 types of spin orientations, particularly the domain formation, and they are classified into 3 types of materials: ferromagnetic, antiferromagnetic, and ferrimagnetic mainly, but all of these things come under the category of ferromagnetism. And so, here on the left side we have randomly distributed spins corresponding to paramagnetic material, whereas in ferromagnetic material we have all spins aligned parallel in one particular region, which we call as magnetic domain or ferromagnetic domain. We will see a little later this. But in the case of paramagnetism, these spins or magnetic dipole moments are orienting randomly, and if we average out over time, it yields 0 net magnetization, whereas that is not the case for ferromagnetic materials. In the first category, we have all spins aligned with equal magnitude, whereas in the second category, antiferromagnetic materials, we have the spins alternatively orienting in opposite directions, so that mostly they cancel each other, but if at all there is any uncompensated spin, that will contribute for feeble magnetism. Whereas in ferrimagnetic case, we have unequal magnitude spins, magnetic dipole moments orienting in the opposite direction alternatively as sketched here, and this will contribute a magnetism in between antiferromagnetic and ferromagnetic. And this is about spontaneous magnetization of some transition metals and rare earths, for example. This is also telling about the temperature behavior of magnetism. And these transition metals at low temperature are ferromagnetic, and at room temperature also ferromagnetic, whereas at high temperature they behave as paramagnetic. That means the magnetism is considerably lost for these materials. And for rare earth materials, these gadolinium and Tb and so on, these materials behave as ferromagnetic at low temperature, whereas at room temperature they are antiferromagnetic except for Gd, and at high enough temperature they behave like paramagnetic. So, magnetism is again considerably lost here. Now, if we consider ferromagnetism in a little more detailed manner, then this may be thought of as a special case of paramagnetism, in which the individual spin magnetic moments interact with each other, thereby forming an alignment, or in other words, these magnetic moments are coupled. Now, the uncompensated spins in individual atoms of a ferromagnetic material may couple either directly, that is direct exchange we call, or through an intermediate anion, usually oxygen or so, and this is called the super exchange interaction between spins, and that contributes to quenching of spins along a particular direction, developing ferromagnetism. So, in such a ferromagnetic material, a net magnetic moment due to coupling of spins in a preferred orientation occurs, and like with the paramagnets, these ferromagnets have strong positive magnetic susceptibility, and the magnetic susceptibility for ferromagnets is considerably larger than paramagnets with the positive sign. Now, unlike paramagnets, when the applied field is removed, these ferromagnetic materials retain a component or a fraction of magnetization along the direction of the applied field, and this magnetism remains permanently almost, and this susceptibility is not dependent on temperature in a way that follows the Curie law. It is a slightly different behavior, which we will see a little later. Then, the temperature dependence of ferromagnetism is as follows. Because the ferromagnetism results from the interaction of atomic magnetic moments in materials, there is an exchange energy associated with coupling of the spins, and at room temperature this exchange energy is much greater than the energy due to randomizing thermal effects. That means the thermal energy kBT is giving rise to thermal agitation of the electrons, and therefore, the spins tend to orient randomly, and hence net orientation along the direction of the applied magnetic field is decreased. So, if the thermal energy exceeds the spin coupling or exchange energy, then the coupling breaks down and the material behaves as a paramagnet. So, this temperature at which such a coupling breaks is called Curie temperature, and in the case of antiferromagnetic materials, similar temperature is called Néel temperature. And this gives a sketch of how the magnetic susceptibility, that is ferromagnetic susceptibility, behaves with the temperature, and this is compared with the paramagnetic susceptibility as a function of temperature. So, at high enough temperatures, both the magnetism, that is ferromagnetism and paramagnetism, nearly vanish off or die off, and they behave similarly, whereas at low enough temperature there is a large difference between the Chi behavior of paramagnet and ferromagnet. And the point of sharp fall at ferromagnetism is called the Curie temperature along the temperature axis. Now, the interaction between spins of electrons is an exclusively quantum mechanical effect, and there is no classical analog in fact. But the materials mentioned here show strong interactions between spins and the ferromagnetism in elemental crystals. In compounds, however, many more substances exist with spontaneous magnetization, which come from the coupling of spins. And to account for such a coupling of spins and development of internal field, and hence the determination of Curie temperature, there was an attempt earlier proposed by Weiss, and this is sheerly a classical attempt, and this is very well known as Weiss mean field theory, and based on this quantum theories were developed and quantum concepts were put in, and hence the relations were a little modified later. But this theory is the one which accounts for the coupling between the spins in the first hand. So, it is a simple theory in principle, and this is often called as Weiss mean field theory, and it starts with an assumption that we substitute elusive spin-spin interaction between electrons by the interaction of spins with a very strong magnetic field. In other words, we can pretend that in addition to the external field, there is a built-in magnetic field which we will call as the Weiss field. The Weiss field will tend to line up the magnetic moments along the direction of the applied field, and we treat the ferromagnetism as an extreme case of paramagnetism in the present one. And the schematic diagram gives how the spins are aligned parallelly, and this accounts for the spin-spin exchange. And here of course, spin-spin exchange is not explicitly accounted or mentioned, but in presence of an external field, it shows how the magnetic spins are aligning in this region, and this region where the magnetic spins are aligning parallelly is called a spin domain. So, here we see anodized state plus Weiss field gives rise to alignment plus external field. So, in presence of external field there is an alignment, here also it gives similar thing, but in this case spin-spin interaction is considered, whereas here Weiss field is considered. This is somewhat more towards the quantum mechanical aspect, and whereas this is the classical aspect. This is the difference between classical and quantum. So, we start with the paramagnet with the n ion spin S. Then suppose there is some local interaction which behaves like a local magnetic field, which you can write as BE, where B stands for magnetic flux, and B can be written as constant multiplying the magnetism developed in the material, the net magnetism M developed in the material, and this is what called as mean field approximation. And what we see here is a sketch of how magnetic spins are oriented parallelly in a particular region in the material. This particular region in the material is called a domain, magnetic domain, where the spins are aligned parallelly. Here this spin direction is different, here this is different, and so on. So, initially such directions are random, whereas once we apply strong magnetic field and if all the spins have interacted with each other, and once all such interaction is over, then the spin directions of all these domains will be parallel, and so we have ultimately the entire material becoming completely magnetized along the direction of the field. So, here we see about phase mean field theory. Here mainly the local field or local magnetic field experienced by a material is written as the external field applied plus Weiss field which is present in the material. So, the magnetism in the material is a combination of these two, external plus the Weiss internal field. And here we write this Weiss field as some constant multiplying the magnetic polarization vector J. Actually, H Weiss is a kind of fictitious field, and we treat it as an internal field, and this H Weiss is written like this with a parameter W, and this parameter is called Weiss factor. J is the total magnetic polarization. Now, the Weiss factor is a very important one. So, it contains almost all the local effects lumped together. Mu naught of course is the vacuum permeability and the interaction between the spins that leads to ferromagnetism. So, all the three factors are put into this W. So, if you know this W, then we can determine the H local, and hence we can work out the chi, that is magnetic susceptibility, and here a spin orientation corresponding to ferromagnetic and antiferromagnetic. This also gives different types of mean fields which give rise to the spin orientations in different manner, but all of them contribute to ferromagnetism. So, this is simple ferromagnetism, this is simple antiferromagnetism, and this is simple ferrimagnetism, whereas this is so called canted antiferromagnetism, and this is all about helical spin array. Now, we again continue with the Weiss field theory. Here the potential energy W of a magnetic moment M placed in an external magnetic field H is written as minus M multiplying mu naught and then H plus H Weiss and cos phi, where cos phi is the component of this quantity of the spin along the direction of the field, and phi is the angle between this M and the applied field H or B. So, we have this, and this is replaced by W dot J, and here we take account of Boltzmann distribution or Maxwell distribution of energies. Capital N refers to the number of spins which have this W potential energy given by this Boltzmann distribution, and here for W we write this above expression and proceed with. So, the magnetization M now becomes M is equal to this N multiplying M into L of eta, where eta is represented by this quantity, and L of eta is actually a function called Langevin function, and this we have seen in paramagnetic theory also. And the total polarization now is written as mu naught multiplying this M, where mu naught is vacuum permeability, and if you write for M here, then we get this, and this L of eta is actually cot H of eta minus 1 by eta if we work out. This also we have seen Langevin function in the treatment of paramagnetism. What we want is actually the magnetic polarization J, which is a function of the external field H. But here we have actually a kind of transcendental equation for J, in which we cannot write down J explicitly. So, we have to go for some graphical solution or numerical solution or approximations. Now, we start with such things. So, here is an easy graphical solution for the above equation. Actually, we have two equations for J, and the argument of Lagrangian function is this. We consider this first. Then from that we can write down J. This is one equation. This is simply a straight line equation because J is proportional to H, where H is a variable, this is a constant. So it is a straight line with a negative slope. Now on the other hand, we have the equation for J in terms of the Lagrangian function as such. This is the one. So that is second equation. So we draw both the functions in a J eta diagram like this. So J is plotted here, J is here, and the first equation is this. So if you plot it, actual J with the Lagrangian function goes like this, following Lagrangian function, whereas the J equal to this constant minus H by omega, sorry, H by W is a straight line which goes like this. So for different H values, we can draw different straight lines. Now these points refer to the solution points. These are the yellow points. For H equal to 0, we have two solutions. Yeah, one for J equal to 0 and the other for large J. Now for J equal to 0, the solution is unstable. It disappears for an arbitrarily small field H. Hence, we are left with a spontaneous large magnetic polarization without an external magnetic field, and this is the case of the second choice. So we first note that the switching on an external magnetic field does not have a large effect, that is J increases somewhat, but for realistic values of H by omega, the change remains very small. This is one point. Then the temperature dependence of J, by looking at the straight lines, if we do, then we see that for T going to 0, the intersection point moves all the way out to infinity. So that means all the dipoles are lining up along the field, and so L of eta becomes 1. So we get a maximum value for J, that is saturation value given by Nm mu naught. But for high T, this argument becomes smaller, that is eta. This eta becomes smaller for high T, and so the Lagrangian function becomes almost 1 by 3 for small eta, and in that case J equal to 0 is a point where both the solutions merge. And not only that, at a tangential region, the straight line as well as the curve with L of eta both merge, and so we have fairly good range of temperature where this approximation holds good. And we can work out a critical temperature from this, and this is a temperature above which the ferromagnetism disappears, and this is called as Curie temperature, and that is obtained by taking dJ by d eta and apply the limit eta tending to 0. Then we have this value for this quantity, that is slope of J with eta goes like this. From the above equations we can get Tc like this. And since for T greater than Tc, that is for eta less than 1, we have L of eta going as eta by 3, we get for J as this with the denominator factor 3 kT here along with numerator multiplying factor H plus W dot J. And if you do some algebra, then with this we can get an expression for J with T greater than Tc as Nm square mu naught square by 3k, that is this entire quantity, with a multiplicative factor T minus Tc in the denominator, and of course there is H in the numerator. Then we can work out chi from that. So chi is actually j by h, and therefore coefficient of h in the above expression is the expression for chi, that is the susceptibility, ferromagnetic susceptibility. This is a famous Curie-Weiss law, and this is also a Curie law for the paramagnetic regime at high temperatures for ferromagnetic materials. So, with that we have successfully derived the expression for chi of ferromagnetic materials by using Weiss mean field theory. Now, coming to summary, we have understood the difference between para and ferromagnetic materials in the present lecture, and also the nature of internal effective magnetic field which is developed inside the material in presence of an external field is also analyzed and understood to some extent, and we have also derived expressions for the Curie temperature and also derived Curie-Weiss law. Then we have a few questions to ponder. What is the main reason for ferromagnetic ordering? And what is called mean field due to Weiss? That is, what is the mean field proposed by Weiss? Then what is the limiting criterion for this mean field approximation to hold good? And thank you.